In this video, we will learn about Ka and Kb, the acid and base dissociation constants. We will learn how to write their expressions and practice calculating their values for some acids and bases. What are Ka and Kb? Ka and Kb are equilibrium constants for the dissociation of weak acids and bases in solution, usually aqueous solution. Ka is the acid dissociation constant, sometimes known as the acid ionization constant, and Kb is the base dissociation constant, or base ionization constant. The value of Ka or Kb indicates the strength of an acid or base. Ka is a measure of the strength of an acid in solution, and Kb is a measure of the strength of a base in solution. Let's imagine this diagram represents an acid or a base, which breaks apart or dissociates in solution into ions. When all of the reactant dissociates into ions, we say that that acid or base is strong. When some of the reactant dissociates into ions, and some of the ions reassociate to form the reactant, we say the acid or base is weak. An equilibrium is formed when a weak acid or base dissociates in solution, and therefore we can determine the equilibrium constant for that acid or base in much the same way as other equilibrium constants are determined. Let's derive a general expression for Ka, the acid dissociation constant. To derive a general expression for Ka, we need a general reaction equation for a weak acid Ha dissociating or ionizing in solution. When a weak acid, Ha, dissociates in aqueous medium, the reaction equation is Ha plus H2O reacting reversibly to give A minus plus H3O plus. The hydronium ion produced comes from the reaction of water with a hydrogen ion from the weak acid Ha. Water plus a hydrogen ion forms the hydronium ion. We can derive the equilibrium constant for this reversible reaction in much the same way as other equilibrium constants are determined. K is equal to the concentration of all the products multiplied by each other divided by the concentration of all the reactants multiplied by each other. Substituting the products and reactants from our general reaction equation, we get the concentration of the anions A minus multiplied by the concentration of the cations, in this case the hydronium ions H3O plus, divided by the multiplication product of the reactant concentrations. Square brackets mean concentration in terms of molar units, or molarity, which is moles per liter or moles per decimeter cubed. When the solution is dilute, the concentration of water is very large relative to the concentration of the other species and is essentially unchanging. Or at least we assume that the concentration of water doesn't change. For this reason, we do not include the concentration of water in the denominator. Instead, we make its concentration a constant, lowercase k. If we then take water's constant to the left-hand side, we get capital K multiplied by small k equals the concentration of the products multiplied with each other divided by the concentration of the weak acid, and the left-hand side value we call Ka. This is the general expression for the acid dissociation constant Ka. Because we don't need to consider water's concentration, we can rewrite this reaction equation more simply. Ha in equilibrium with its ions, A minus and H plus. Since we have removed water, we can change the hydronium ion to a simple hydrogen ion. For this reason, we might sometimes find the Ka expression without a hydronium ion, and instead a hydrogen ion will be in its place. The equilibrium constant for a weak base dissociating in water, Kb, is derived in much the same way. Let's simplify by removing water right from the start so we don't need to do a long derivation. And we get the general reaction equation for a weak base, BOH, which is BOH dissociating reversibly into its ions, OH minus the hydroxide ion, and B plus. Then the base dissociation constant Kb is equal to the molar concentrations of the ion products multiplied with each other divided by the molar concentration of the weak base. This is the general equation for the base dissociation constant Kb when a weak base dissociates in aqueous medium. Let's put the acid dissociation expression back and have a look at these two expressions. Because the base and acid are weak, they only dissociate to a small extent, and sometimes the denominators are referred to as the original or starting concentrations. But we must remember that these expressions are actually for equilibrium situations. Ka and Kb, like other equilibrium constants, depend on temperature. Temperature influences or affects how far an equilibrium sits to the right or to the left. In other words, the equilibrium will sit more to the right or more to the left, depending on whether the forward reaction is endothermic or exothermic, and depending on the temperature under which the equilibrium exists. For this reason, 25 degrees Celsius is a common temperature at which Ka or Kb is determined. In this way, these values have meaning when they are compared with each other, or have meaning when the temperature changes. Now let's practice writing Ka and Kb for a weak acid and a weak base. HCN, or hydrocyanic acid, is a weak acid. This is the equation for the dissociation of this weak acid in solution. We can write the acid dissociation constant for this acid, Ka, is equal to the molar concentrations of the ion products multiplied with each other divided by the molar concentration of the acid, HCN. Note that because the mole ratio of H plus to Cn minus is 1:1, these two concentration values will be the same. If the stoichiometry was not 1:1, the concentrations would not be the same. However, the stoichiometry of the products is usually 1:1, even in the case of polyprotic acids, which lose their protons one at a time, forming different equilibrium reactions. In other words, they undergo a stepwise dissociation. But this is a discussion for another video. When ammonia gas dissolves in water, ammonium hydroxide is formed. This is a weak base. Ammonium hydroxide dissociates to form an equilibrium with its ions, NH4+ and OH-, the ammonium and hydroxide ions. We can write the Kb expression for this base dissociation as follows. Kb is equal to the molar concentrations of the ion products multiplied with each other, divided by the molar concentration of ammonium hydroxide. In this example, we again have a molar ratio of the product ions 1:1, and so we know these values are the same. In a moment, we will practice calculating the actual value of Ka for a weak acid. But first, let's investigate what the size of a Ka or Kb value actually means. What information does it give us? What does the size of Ka or Kb tell us? We know that Ka or Kb is equal to the molar concentrations of the products multiplied with each other divided by the molar concentration of the reactant. If Ka or Kb is a large value, this tells us that the numerator value is large relative to the denominator value. In other words, the products of the dissociation reaction are favored, meaning the acid or base is relatively strong in that it dissociates to a large degree. Now I say relatively because Ka and Kb are only for weak acids and bases. But even weak acids or bases have relative strengths. When Ka or Kb is a small value, this tells us that the numerator value is small relative to the denominator value, meaning the acid or base in its undissociated form is favored. That acid or base is relatively weak, meaning only a little bit of it dissociates. So again, Ka or Kb size indicates or is related to the acid or base strength. Now it's time to practice. Calculate the Ka value of a 0.2 molar aqueous solution of propanoic acid with a concentration of H+ ions of 1.62 times 10 to the negative 3 molar. Give your answer to 1 decimal place. A. 4.8 times 10 to the negative 4 moles per liter. B. 6.6 times 10 to the negative 5 moles per liter. C. 1.6 times 10 to the negative 2 moles per liter. D. 5.2 times 10 to the negative 7 moles per liter. Or E. 1.3 times 10 to the negative 5 moles per liter. Propanoic acid is CH3CH2COOH. We know this from the name stem prop, meaning 3 carbons in the chain, and telling us there are single bonds between carbon atoms, and the suffix oic acid telling us this is a carboxylic acid with a carboxyl group. Propanoic acid is a weak acid, meaning in solution it dissociates to a small degree, forming an equilibrium according to this equation. The dissociation products are the ions CH3CH2COO- and the hydrogen ion. We are asked to find Ka, the acid dissociation constant for this weak acid. We are told the starting concentration of the acid 0.2 molar, and we are told the hydrogen ion concentration in solution 1.62 times 10 to the negative 3 molar. Let's start by writing the expression for Ka. Ka is equal to the molar concentrations of the ion products, which are the propanoate ion and the hydrogen ion, multiplied with each other, divided by the molar concentration of propanoic acid, the reactant. Square brackets refer to molar concentration, or molarity, which is moles per liter or moles per decimeter cubed. We are given the denominator value in terms of molarity, 0.2 molar, and we are given the hydrogen ion concentration in terms of molarity too, 1.62 times 10 to the negative 3 molar. But we don't know the concentration of the propanoate ion. However, from the balanced equation, we know that the molar ratio of the anion to the hydrogen cation is 1:1. And so the concentration of the propanoate anion must be the same as that of the hydrogen ion. Let's now put in our values. We get 1.62 times 10 to the negative 3 molar for the concentration of the anions, multiplied by 1.62 times 10 to the negative 3 molar for the concentration of the hydrogen ions, divided by 0.2 molar, which is the concentration of propanoic acid. And the value of the answer is 1.31 times 10 to the negative 5. These two units can cancel, and so the unit in the answer is molar, which is moles per liter. Note that sometimes Ka and its relative, Kb, the base dissociation constant, are expressed without units. We were asked to give our answer to 1 decimal place, so let's round off. And we get 1.3 times 10 to the negative 5 moles per liter, which corresponds with answer option E. The Ka value for this propanoic acid equilibrium is 1.3 times 10 to the negative 5 moles per liter. Let's sum up what we've learnt in this video. We learnt about Ka and Kb, the acid and base dissociation or ionization constants. We saw that for a weak acid in solution, HA, dissociating to form an equilibrium with its ions, A- and H+, the Ka expression will be the molar concentrations of the ion products multiplied with each other divided by the molar concentration of the reactant, which is the weak acid. And for a weak base, dissociating into its ions in solution and forming an equilibrium, the Kb expression is Kb is equal to the molar concentrations of the ion products multiplied with each other divided by the molar concentration of the reactant, which is the weak base. We learnt that Ka and Kb, like other equilibrium constants, are temperature dependent and change according to the temperature. We saw that this is because the values in the numerator and denominator of a Ka or Kb expression will change as an equilibrium shifts due to temperature change. We also learnt that the value or size of Ka or Kb indicates or is a measure of the acid or base strength.